Welcome to session, oh, it's not on there. So session AP. Thank you, Kevin. Session AB, Modernizing zOS source control and build without JCL. Dang, 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 a user experience. So I'm pleased to be able to hand over to Suba and Kevin. They're going to moderate their own questions. So if you can pop them in the chat, that'll be brilliant. So over to yourselves.
Okay, thank you, Stuart. My name is Kevin Cogley. I'm a senior software developer here at Dynatrace. I've been in the mainframe business for well over 35 years, mostly assembler coding. I do some C coding and some COBOL for testing, almost exclusively with independent software vendors.
All right. Hello, everybody. My name is Subha Ramachandran. I'm a senior software engineer at Dynatrace. I work in the mainframe agent team at Dynatrace. I have over 15 years of experience in mainframe. And then on the distributed side, I have a couple of years experience worked in Java programming, web development, C programming, etc. So today I'll be co-presenting with Kevin. Thanks for joining us today.
Okay. Basically, what we're going to talk about today is a high-level overview of what we've done at Dynatrace, Suba and I, over the past 2 or 3 years to modernize our development environment. We're going to talk about the tools and technologies we used, what our build infrastructure looks like, what the day-to-day developers use, what our timeline was, all the challenges we have, and a little bit of demo. Actually, the whole GMake part's going to be a demo, so you can see what we do. At the end of this is going to be our emails, and we do have a sample file that we can send out if you'd email us. And this sample includes all the stuff that we're doing today. You can build C, you can build assembler, you can build COBOL programs from simple files that we're going to send you. Why we wanted to migrate to Git. So when Dynatrace first started here, when the mainframe, we were using a product called Endeavor. Endeavor was a good product for source control. It's been around a long time. It had different stages. We could create PTFs from it. We could do SMP installs, everything we wanted. But Dynatrace has hundreds and hundreds of developers all over the world. Very few of us are mainframe developers, probably about 9 or 10 of us. And everybody else in the company was using more modern technologies like Git and Jenkins and all kinds of other stuff. So we wanted to make our mainframe, or we wanted to see if we could make our mainframe look like all the other developers for Dynatrace in the world. So what we found was Git for zOS, and Suba and I sort of on the side, not as part of our real job, decided that we were going to take this and try to migrate our Endeavor and build environments to Git for zOS. Neither one of us had ever done anything like this before. We both worked with Git, but on different platforms. One of the problems with Endeavor is we had no build automation. Dynatrace has a huge build automation and testing platform built in. We have 2 separate groups in our company that do nothing but build automation and automation testing build. We call it our ATF platform. This was not integrated in Endeavor at all. With Git, it was integrated with the build infrastructure. We could do it all because as far as Git was concerned, for our implementation team and our build teams, it was the same as any other platform. Endeavor, we had a hard time fitting it in with our 2-week sprints. Endeavor was more of a re-release product once a year or twice a year type of thing. Not every sprint or every 2 sprints. Git was really easy to automate. We already had it done. Dynatrace was doing it for all the rest of our products. And Endeavor, the processors where the JCL was a complicated process. And this grew out of years and years of experience. There was overrides in them. There were so many different JCLs for so many different versions of Kix and IMS and zOS that it became very complicated to handle. With Git for zOS, there's no JCL. We do everything under USS. So we decided that we were going to try to do this whole thing. We went out and searched for tools. Basically, we're using Git for zOS. Dynatrace already has a huge subscription to Bitbucket. So we decided that was going to be our source code repository because that's what Dynatrace decided. We're going to use Jenkins as our build automation server, mostly because we already had a whole team of people dedicated to Jenkins, and all the other development teams were using Jenkins. We decided to use gmake for our build control, curl for our file transfers, and all the IBM USS commands for compile and link. We got our Git from Rocket Software. There's a link to the Rocket API tools. We're going to talk about in this presentation, and I'm going to give you some ideas of how to configure all these real quickly. These are more to go back and look at later on if you're trying to do this yourself. Git for zOS needs a profile, a config, directory, and down here at the bottom is how the directory looks. You have a home directory, a profile, a config, and an attributes. Here's a sample Git configuration file. This is more for a test environment, so everybody can have their own .profile when they log on to USS. I suggest when you go production that you take some of these variables and put them as a system variable. And then if you get new versions of Git or new versions of anything, you can change your own private profile to point to the new ones. But everybody else, including your production system, uses the old ones. The Git config file has this green highlighted as the important thing. This changes everything from iOS 8859-1 to IBM 1047 EPSIDIC when it brings it up to the mainframe. So everything is stored out in Bitbucket in the iOS 8859, but every time you do a Git pull, every time you do a Git clone on zOS, it's going to put it in EPSIDIC format. The other big thing is that the Git ignore, Git attributes all have to always be in 8859. Git expects those to be in ASCII type of formats. The last one's just your config. This is your username, your domain name, things like that. The next thing we use is Bitbucket. Basically, we're licensed for Bitbucket from the company. It features pull requests. This is one of our favorite features. I'll show you later. When you push something up to Bitbucket, you put out a PR, you get reviewed by your peers. They can give you comments. They can approve it before you merge it. And then when you merge it in, it kicks off the whole build process. The Bitbucket configuration for zOS, basically we had all our stuff was in PDSs, as you can imagine, all our source code, all our JCLs, all our samples. So we used ocopy to move everything to USS on our Z. After that was done, then we went ahead and made it into a Git repository by just doing the simple git init, git adds, git commits, and then finally a git push to Bitbucket. And that made our initial repository out in Bitbucket. There's two ways to pull things from Bitbucket, SSH and HTTPS. All our developers here now use SSH. The big thing is you have to set up your own RSA public key. You have to push it up to Bitbucket as in your user profile. You can also connect if you're outside to HTTPS and use username and password if you want to. This is what our development everyday environment looks like right now for all our zOS developers. Basically, we have our server on Bitbucket. This is our repro. This is all our current code with all our branches. If you were a developer, the first thing you do if you're brand new is you do a git clone. If you've been developing for a while, you get a git pull. So you do all the basic Bitbucket stuff back to your USS branch. So now on your USS, you have all the current code that everybody's merged into the server. You go ahead, now that you have this, and you make your changes, your fixes, add new modules, whatever you're going to do. You do a git checkout -b for branch and make your own branch. If it's a problem, we put the problem number in the branch. If it's a new feature, we'll put the feature name and JIRA ticket in the branch. We'll do a git add for our new changes, and then we'll do a git commit with a message. And after we commit it and we're sure about it, we'll push it up to the Bitbucket server. And we'll put out a pull request, a PR, and we'll tag different members of our team to look at this and give it a peer review. Once they've approved that or kicked it back and we've changed it and went through this whole add, commit, push process again, we'll go ahead and do a git merge. And then the git merge is going to go ahead and kick off our Jenkins server. And Jenkins is an open source automation server. It provides our pipeline infrastructure for building, testing, and deployment. The reason we're using Jenkins is because Dynatrace has been using Jenkins for years. We have a whole EP team that takes care of this. We use completely Jenkins's code. For zOS, I started out, and Suba helped me a little bit. We were pulling down Jenkins and using the zOS plugin. And the zOS plugin allows you to use JCL and other things with Jenkins, and that's worked fine. We did some tests at it, but when we moved it to production, our Jenkins team took it off and made it Jenkins's code. So as far as they're concerned from Jenkins, we are absolutely no different than any other group in Dynatrace. They have no clue that we're a mainframe except for our HTTP connections and our IP addresses. Jenkins has a basic Jenkins file. This is a text file containing the pipeline definitions. It has its own syntax, as does everything that we ended up working with. A sample Jenkins file, a simple one, is like init, build, and deploy. So here's what a Jenkins file would look like. So if you're setting up Jenkins for the first time, you'd put in your name, your host, and then your pipeline stages. And like an init, this would be like your Git pull. Your build would actually run your build shell scripts on USS, and then your deploy would actually put your artifacts wherever you want them. The next part of this is we use inside Jenkins is gmake. And Suba's going to take it from here, and we're going to do a little demo, and we're going to show you what gmake looks like and really get into this, because this is the part that helps us build without the JCL. This is where all the work from the zOS end is done.
All right. Thanks, Kevin. So I'm going to be talking about gmake and the other tools that we use in our build environment. So gmake is a powerful tool in Unix that you can use to run the build, to build your applications. So what makes it powerful is that a gmake can automatically detect the dependencies, and then it can only build the modules that got updated based on the timestamp. So it keeps track of the timestamp and then builds only the modules that got updated, and then also it builds the dependent modules for your update. So how gmake does this is based on set of rules. So we write the rules in a file called makefile. So makefile is similar, equivalent to a script. I guess, Kevin, we see the Explorer now. Could you switch back to the presentation, please? Okay, thank you. So yeah, so all the rules gets written into the makefile. So the syntax for makefile is kind of different, but you can think of it as a scripting file. And gmake, you can use gmake to build any programs written in any language, as far as you could run the compilation of the language in the Unix environment. You could use gmake to do the build. And we got the gmake from the Rocket software as well. Next slide, please. Okay, so the next tool in our list is curl. We use curl to upload our files, the build artifacts from Unix, from our Unix environment to the Artifactory server. So we got the curl from Rocket software as well. Could you hit next, please? So here we have given the set of parameter, set of variables that you need to define in your profile to point to wherever curl is at. And then, yeah, so here we show a quick example of curl command that is used to put a file from the Unix, from the USS environment to a server wherever you want to upload to. Next, please. Okay, so in this slide, we want to show you how all these tools are put together to run our build. Basically, how all these tools come together to make this build suite, make this automation possible. So on the left, we have the Bitbucket server where we have the code repository stored at, and to the extreme right, we have the Artifactory server where we want to upload our build artifacts finally after build is complete. And then at the top is the Jenkins file. So Jenkins file has 3 stages in it, which are like simple 3 stages: init, build, and deploy. Basically, Jenkins file is going to drive the build automation. So when a developer pushes any change to the Bitbucket server, it gets merged to the code repository. So this changes the timestamp of the repository, and the timestamp is what triggers the build automation. Jenkins triggers the build automation and then refers to the Jenkins file, and then follows each of the stages. So the first stage in the Jenkins file is the init stage. So here's where we are prepping the build environment in USS. So in the init stage, it runs git pull. Basically, git pull will bring in the updated repository from Bitbucket server to the mainframe USS environment. Next, please. Yeah, so with git pull, we got the repository to the USS. So now that the init stage is successful, Jenkins proceeds to the next stage, which is the build stage. So in the build stage, we run the gmake command. And gmake internally, it uses the make file, the build rules from make file, and then the make file calls set of scripts, shell scripts, which we will show you in our demo part. So gmake uses these build rules combinedly from the shell scripts, and then it runs the compiler and then the link-headed commands, and then it builds the load modules. So along with load modules, just like when we build in JCL, we get the link listing, compiler listing, link listing, object modules, load modules. We get all these as a product of gmake build. Along with this, we also get another file called as dependency file. We will also show you the dependency file in our demo part. So all these are zipped up and then created as an artifact. And then once the build is successful, Jenkins proceeds to the deploy step. So in the deploy step, we run the curl command to do HTTP put from the USS to the Artifactory server. So this is an overall view of how build automation takes place here at Dynatrace for mainframe. So yeah, we can proceed to the next slide, please.
Super.
Yes.
What sort of Artifactory repository do you use? Is it called the general one or something? And what format do you store stuff in there as?
I believe we use JFrog. Is that
We
right?
use JFrog. Yes, we use
JFrog
JFrog.
Artifactory.
Yeah, within Artifactory though, there are different types of repository. You know, they have specialist ones, and I was just wondering what format you store them in, whether it's a tar or a PAX format or something.
Yeah. So we store the Artifactory in Maven format. So we store in POM file. We store it as a POM file, and we also have we also generate PAX file, which is our product deliverables. So yeah, we store the artifacts in 2 formats, basically both PAX and POM for Maven.
Beautiful. Thank you very much.
Okay. Yeah, so in the next few slides, we talk about makefile, the syntaxes, and different ways of defining build rules, etc. But in the interest of time, we would like to switch to the demo. You always, you have access to the PPT. So if you have any questions, you could go back and refer to the commands. Yeah, so I think we can switch to the demo now, please.
Okay.
I think we have a question in the chat. Okay, so the question is, I understand GNU is a volunteer for software. What risks should enterprises consider when implementing this, especially as it would impact production environments? I try to take this, Kevin, please jump in if I miss anything.
Okay.
So when we did this effort, we installed it as a free software. But lately, when we did the upgrade, we noticed that it is a paid product if there is some support involved. But so far, we haven't encountered any problem. So it's from Rocket Software. I think it's a trustable vendor. So
yeah, you can actually pay for the Rocket implementation, or you can download your own or another port. We try to match it up with the GNU GMakes that we run for the rest of the company. The rest of the company uses GMake also in their build environments. So they're as long as you do some adequate testing and or you have a vendor that's actually supporting it, I think you're going to be in good shape.
okay, thanks, Kevin. Hope that answered your question, Atul. Thanks for the question. Okay, so what we see on the screen is the zOS Explorer. I think we're seeing the presentation again, Kevin. Okay, there we go. Thank you. All right, so this is the zOS Explorer that's connected to one of our LPARs. And what we see on the left is the USS environment. So here we have a code base written purely for demo purpose. We have written a few programs in assembler, C, and COBOL, just to show how we build these programs. And some of these programs make Kix API calls as well. So we would like to show you how we build these programs through GMake. So yeah, so here we have two folders, build and source. So in the source folders, we have all the source codes, and then the macros for assembler. And then in C, we have the header files as well. So that's our source folder. And then up above is our build folder. So here's where we have all the build rules, the make files. We have the make files, and then we also have the scripts, basically the shell scripts, which call the USS command. And then up above in the resources is where we are going to store the compiler listing, link listing, the object files, etc. And along with that, as I mentioned before, GMake also generates what is called as dependency file. So the dep folder is going to store the is where we are going to store the dependency files. And the load modules, we are going to store it in a PDS file. That way, it's easy for us to integrate in our automation framework, test automation framework. So that's why we are storing it in the PDS, but you could also store it in the USS path as well. It's your preference. So yeah, so the data sets tab on the left shows our PDS data sets where we are going to store. So we have two PDSs, two data sets. One is a PDS and then the other is a PDSC. So PDSC is where we are going to store the COBOL load modules. And then the PDS is where we are going to put the assembler and the C programs load modules. Okay, so now we can switch to the Unix tab, please. Okay. All right. So first, we would like to start with showing how we build COBOL modules. So to begin with, I would like to show the scripts. So for COBOL under scripts, could you expand the COBOL directory, please? Yeah. Okay, thank you. So in COBOL, we have two scripts. Those are plain old shell scripts. So in the COBOL compile script onto the right, so if we scroll down on the COBOL compile script on the right, so there is cob2 command. So cob2 is a USS command. Cob2 is basically a COBOL compiler that you can invoke from USS to build any COBOL programs. So similar to COBOL compiler in JCL, where you pass the compiler options and you pass the path where you want to store the listing, where you want to store the object module, etc. We can do exactly the same things here with the cob2 command. So you can pass the COBOL compiler options and then the listing path and where you want to place the object file, everything as parameters for cob2. So this will compile your COBOL program and then it generates the listing and the object modules. Notice that for COB2 to compile your COBOL program, your program should have the suffix .cbl. So that's the extension that you want to put for your programs for COB2 to recognize it as a COBOL program. So this script does the compilation of the COBOL program. And then the second script that we have is COBOL link script. So in this script, we invoke a USS IBM USS command LD. So LD will link edit all the object modules, and then it generates the load module. So like any link edit JCL, for LD command, you can pass the link edit options, and you can pass list of includes for your .os, and then you can also specify if you want to include order or entry clauses in your link edit job or for LD here. And then the load lib there, where it starts with 2 forward slashes and then a quote. So that's the format that we need to specify if you want to place the object, if you want to place the load module in a PDS. Whereas if you want to generate the PDS in a USS path, you don't have to put the 2 forward slashes. It has a different syntax. I forget what the syntax is at the moment, but the 2 forward slashes is to place the load module in a PDS file. So these two are the scripts that we have to compile and link edit a COBOL program. So now we can jump to the make file to see how a make file looks like. A COBOL make file. Yeah, so COBOL make file is the make file that has set of rules in order to build the COBOL programs. So the build rules section shows list of targets, the build targets that will be run one after another by GMake. And then, so these are special syntaxes that we use for Makefile. So this syntax that's highlighted over there with percentage, and then down below there is $, lesser than symbol and everything. So these are all makes syntaxes, and we also use GMake's keywords like base name, not directory, etc. So all these put together, what GMake does is that it goes through every program in your COBOL directory, wherever you have your source code. So it compiles, or I would say it processes program one after another. It's like going in a loop, and then it does whatever the target tells it to do. So in this case, the target tells GMake to first call the compiler script COBOL compile.sh, and once that's successful, then it proceeds to the next step, which is calling COBOL link step. So here's where we do the link edit of all the .os that were produced in COBOL compile. And in addition to that, we also have other targets there to clean. If you want to do a clean build, you can always do GMake clean, which will clean up all the previous build artifacts, and then it will do a fresh build for you if you invoke the build target again. Okay, so I think now we can switch to the command, Paddy. So
you've actually got a question, Suba? Or,
oh, okay. All right. Good. I think
if you go back to Stefan.
Yeah.
Shama.
Okay. Just for my understanding.
That's the one. Yeah. Start from there.
Okay. Compiler and linker are also running on USS and not on the zOS part of the machine. Yep, that's right. All these commands that we invoke are USS commands, and they run on USS. And yep. What if I want a real zOS compile and link?
These are real zOS compiles and links. They're the IBM compiler, the IBM link editor. They're just running on the OMVS portion of your Z machine. So if you're in TSO, you can go to TSO OMVS and run these. Here in the panel that I'm showing you, I'm actually putted in to our Z as a USS So the compilers and linkers and everything we're going to show you here are all the true IBM ones that come and are documented out in the IBM manuals.
Okay. Is there an advantage to using these scripts over using JCL, example, performance, etc.? We haven't seen any performance degradations using these scripts, using these USS commands versus JCL.
The big thing is that, like we showed with the make, that you can cycle through everything in a folder, where with JCL you might have to do multiple steps. It's less complicated. I think people that understand Linux understand the scripts better than they understand JCL, especially if they've never been exposed to it. I know our people that do our Jenkins build can look at our scripts and debug them faster than I can, because I've spent so many years on JCL. Other advantages.
It's easy to maintain for sure.
It's easy to maintain once you have the variables.
Yeah, one thing I've noticed personally though is that when we were in Endeavor, so there were different JCLs used for doing the product build, and me as a developer, I would be using a different JCL, so there would be different concatenation, so I could be pointing to older versions versus the production is pointing to the current and late. So there were these kind of problems I faced when we were using Endeavor, but then after we moved to GMake, basically developer build and the production build is using same set of scripts with same Mac libs and everything. So we all are pointing to the same version.
Right, and we all try to use a base version for our base testing. And then I see it's the good old zOS COBOL. We actually have all the COBOLs here that we do test with, but ours we're pointing to the old one.
Okay, moving on to the next question. What is a real zOS compile and link? I think Kevin addressed that. With the good old zOS COBOL compile.
Yeah.
Okay, I think that's a comment.
Yeah, ours is pretty old. That the one we have concatenated in here. But we do test with all the new COBOLs too. And it is cool to have different ways instead of JCL.
Right. Yeah. Yep.
We agree.
All right. Okay. I love the interaction. Thank you for the questions. Okay, so here we're going to show how we do how we build COBOL programs using GMake. So build COBOL is the target that we put in the make file. So that invokes subsequent steps in the make file, which then invokes the COBOL compile script and the link script. So I believe we have two COBOL programs. So first it compiled and then it called the linking. Yep, so both the programs have been compiled and link edited, and then the load modules are now in .load.pdsc. So now we can jump to the data sets and can see if, okay, can refresh. Okay, so these are the load modules that were built using GMake, and there was no JCL involved anywhere. So that's about COBOL build, and now, oh yeah, listings. Okay, so that's our compiler listing. So it's nothing different from compiling it from JCL using the IGY typical COBOL compiler through JCL. So the listing looks exactly the same when you compile using cob2 USS command. And then the link listing is at the top in the link directory. So in the link listing, so in the LD command, you can pass an option called -v for verbose. So we found this to be really helpful when we first migrated to this format. So this helped us to see how if we are getting the order class right, if we are getting the entry right, and what are the includes, the sys libs that are included. So putting the -v option in the LD command really helped us. So we get the JCL that's getting built in the background to do the link edit. So you get these here for troubleshooting. And then if we scroll down, we can see all the mapping, just like we would get a link listing through the HEWL through JCL. Okay, so that's our link listing. All right. Yeah, IGYCRCTL, thank you. Okay, so now we can move on to how we do the build for C programs. What about DB2 processing, pre-processing? Currently, we are not using any DB2 calls in our programs, so we haven't researched much into it. But I'm not sure if any of these commands support DB2. There should be. I don't see a reason why it shouldn't be there, but I don't know. Kevin, you have any idea?
No, we haven't used that. We have DB2 in our test programs, but with our test programs, I don't have those under GMake yet. I don't believe. I think we still use JCL.
Right. Just use the coprocessor.
And for kicks, we do use the preprocessor, and 2 of the compilers have a preprocessor option, but assembler does not. So Suba will talk about that in a little bit. Yeah, translators.
Yeah. Yeah. So for C programs in the scripts, so similar to COBOL in C, also we have compile and link scripts. So some of our sample C programs here make Kix API calls. So we want to do Kix translation before we can proceed to the compilation step. So XLC is the IBM USS command that does basically it does translation, Kix translator, it invokes Kix translator, and then it invokes C compiler, and then it's also capable of doing link edit. So it's all 3 built into one command for C. So for XLC to invoke the Kix translator, yeah, so you may want to pass Kix open paren, close paren Kix as one of the options in the -W. So this will indicate XLC to call the Kix translator. And then what follows after that is the compiler option for C. And then there's -I for include. And the -F, the config it's another config file that XLC refers to. So you can control what DSNs that you want to concatenate in the step lib of your compiler using this config file. So it's an XLC config file. So the document is pretty good. IBM's documentation on XLC is pretty good. And we also found the manual, the man XLC. If you type man XLC in your USS command line, the manual is also pretty elaborate. So that also helped us. And then the -I for the include, and to the right where it says dependency, like $dep/program.u. So XLC command, it automatically generates dependency file. We will show you how a dependency file look in a bit after we run the GMake command to build the C program. So yeah, it's an auto-generated dependency file. Basically, GMake makes use of these dependency files to track what are the dependent programs. Let's say, for example, if you updated a header file, right? And if the header file is used in like 10 programs, say, so if you update one header file, GMake automatically figures, okay, all these 10 programs are impacted. So it recompiles all these 10 programs. So it does that with the help of the dependency file. And then you can pass the program. So like .cbl for COBOL program, you want to suffix the C programs with .c. So this is the format that you invoke XLC for compilation. And then in the C link script, so here again, we call XLC notice the -v option for verbose. So here we pass list of the .os, and then we are going to put the load module in a PDS file pointed by $load_lib. So now we can switch to the make file, C make file. So in the C make file, under build rules, build C is the build target to build the C programs. In our case, some of the programs are Kix C programs. So here, so this is one way of writing make files. So we just want to show you different flavors of writing make scripts. So in this make script, we are calling one program after another. We are not making use of the gmakes looping technique. So here we are calling, we are first calling C program 1. So that's the translate and compile and link edit, and then we are calling C program 2, and then we are calling third program, etc. This is not a very efficient way of doing in Makefile. Say, given a repository where you have like thousands of programs, you cannot do this one after another. But just to show you as an example, if you want to quickly put together a Makefile and then you want to compile one program or two programs at a time, so this is one way to do it. Now we can switch to the PuTTY, and then we can try to do gmake build C.
Yeah, I didn't realize I had all those other programs in. So the first ones are going to work, but I think the second ones are going to fail.
Okay.
The DT ones.
The TCP IP ones.
The TCP IP should work, but the ones after that, if it calls it.
Ah, okay.
So it built the first two.
Yeah. Okay, so the first two programs are were written for demo purpose. The next ones, I think those were Kevin's test programs.
Test.
Okay, so now that we have built it, we can go to the data sets, and then we can see if we have the load modules. Okay, so the C program 1 and 2 are the C load modules. It built successfully, and then we can switch to resources. Okay, so those are our C program listing. Okay, so we have 15 more minutes, sort of. Okay, so and then in the dependency, we can quickly show you the auto-generated dependency file. So notice that for every programs there, you have a .u dependency files, and then on the right-hand side, for the first program, gmake has automatically stripped off the .h files used in that program. So config.h is the only header file apparently this program is using. So maybe we can check the second program, cpgm2.u. Okay, so this program also has only one header file, but anyways, so if we update the config.h, and then if we do gmake build C, it's going to automatically recompile both the programs and rebuild both the programs. So that's the main purpose of having the dependency. And the good thing with XLC is that it will automatically generate these files for us.
Yeah, this is really nice. This is one of my favorite features.
Yeah. Okay. So that's about C compilation, and now we can move on to ASM compilation. So for our ASM source programs, again in ASM, I believe a few of our programs does Kix API calls. So to compile, to build our assembler modules, we want to translate all the Kix API calls first. So we could not find any USS, IBM USS command that does the Kix API translation in an assembler program. So we wrote an assembler program called KixXLAT, which will read through the assembler program, and then it translates all the Kix API call to a DFH call that assembler can understand. So that's our in-house KixXLAT program. So the ASM translate.sh So in that script, we are basically calling our in-house program to do the translation. And after that, the assemble.sh script down below. Yeah, and then if we scroll down. So here, AS is the USS command to assemble our assembler programs. So again, here with AS command, we can pass the assembler options and then the .i to include our Mac lives, excuse me. And then we can pass the path where we want to put the listing, the .os, etc. And yeah, here as well, we want to suffix our assembler programs with .a for our AS to recognize them as an assembler program. So that's the assembler script. And then in the ASM link script, so we call the LD command. So just like COB2, AS will only do the assembly, but not the link edit. So which is why we are using LD to do the link edit. So again, here we do the -v for verbose. I forgot what the -v was for. I'm sure it was also helpful. And then, yeah, so the R mode, A mode assembly options as well. So few of our programs we assemble with R mode, A mode, 24 and any. So here we are placing our load modules into a PDS. So, and then we have order class, and then we also have an entry class with -e. So that's our link edit for assembler object modules. Yeah, other thing that I forgot to mention here is that unlike XLC, AS command does not automatically generate the dependencies. So what we did was that we manually created the dependency file for all our assembler programs. So in our project, we have about like hundreds of, if not thousands of assembler programs. So what we did was that we made use of the listing that was generated through JCL. So at the bottom of the listing, you could see a list of Mac lives that this assembler program is using. So we wrote a little Java utility that will read through all these listings, and then it will grab all the Mac lives. And then we created the dependency file in a format that GMake would understand. So here in this case, for example, in the demo program, so Mac ASM .a assembler program refers to two macros called Mac1 and Mac2. So this is the format that GMake expects the dependency file to be in. So this is a handwritten dependency file for assembler programs. So that's one point there. Then we can do GMake build ASM, I believe is the target name. Okay, so first goes the translation, Kix translator step for all the ASM programs, and then proceeds to assembling, link editing. Okay, so you should see the load modules of all these assembler programs in the PDS dataset. Okay, so those are our load modules of our ASM programs. So that concludes our demo. So if you have any questions or if you would like to see this demo code base, we would be happy to share. Please email us. Our email ID is given at the end of the slides. So with that, thank you for listening. I'm going to hand it over to Kevin.
Okay, yeah, the base share file that we were showing you, how we started with everything empty, we're welcome to share with anybody that emails and asks for it. We have permission to do that. Also included in that is our CICS translator. It's not, basically what our CICS translator does is we wrap around the IBM Kix translator from the assembler from the assembled JCL. Basically, we just build all the inputs that it wants, and then we call the IBM translator. and then it puts out the output just like it would if you call the translator from JCL. So we have about 10 minutes left. I just want to talk about the timeline. This took us longer than we thought it was going to. Basically, we had to install the necessary tools, which I've never done before, so that was exciting. Move the source to Bitbucket, that was the easy part. Write the Jenkins scripts. This was with the JCL. This is where I was talking about we used the zOS add-ons, plugins for Jenkins, just for testing to see how it worked. We wrote the shell scripts using the USS commands. And then we wrote the make files to invoke those shell scripts and use all the other gmake fun things that Suba just talked about. And then our Jenkins team actually went and created the Jenkins pipeline to integrate with all the other build infrastructure. So we look no different than any other build going on in our company. And then for a while, we ran parallel with Endeavor before we went production. So we just made sure that every output and every sprint from the new Jenkins pipeline matched up with Endeavor. We were actually doing pushes and pulls to both into Endeavor and into Bitbucket for a while until we were satisfied and cut over completely. There's a question: are you able to maintain deploy history for audit purposes and for feedback? Yeah. Our deploy history is an Artifactory, and it is complete back to the very first day that we started these tests. We have everything. It gets packed and then it gets pushed away. So every build that happens, we have every artifact, every listing, every compile, every link from everyone, and every output from everyone there. So we can fall back really easy. With Git, you can always go back branches, you can rebase. We have a new, for our mainframe product, we have a new release every 2 sprints. And we can always add on and put maintenance on in the middle of a sprint if we have to do a backport or something like that. It makes it really easy. It's distributed in a PAX file. So if you have to backport, you make a backport branch, you push it out to Bitbucket, you run all your builds, you let it go through all our QA testing, which takes a couple days. And then you can push a new PAX file out or give a customer a PAX file to try to make sure it fixes their problem. The challenges we ran into, at first we had some ASCII to EBCDIC conversion issues, especially with the Git commands, like git stash didn't work at all. There's a bunch of Git commands we found, and we actually went in and fixed ourselves. A lot of these have been fixed in the meantime. And as you upgrade versions of Git, you may run into some of these type of things where they just hadn't been tested yet, or something's changed and it doesn't work on your version of zOS or whatever. The initial setup environment, the SSH to HTTPS, we had to figure out some stuff with SSH. We got that working just from our mainframe out to the Bitbucket server. All our experienced zOS developers needed training, especially Git training. We've all been using JCL and things like Endeavor, that type of source control forever.
Kevin,
there's a question.
We have a question. How do you secure who can do the builds?
For production builds, there's only one zOS user ID that's allowed to do it. And it's controlled through Bitbucket and through your Bitbucket sign-on. So I can sign on to Bitbucket, or Suba can. There's a few people in our group that can go in and manually kick off builds. The automated builds are all done through one user ID. So they're controlled that way, and they can tell who kicked off the build, whether it was an automated build from a merge or Suba and I kicked it off. Does that answer your question? It's just RACF secured on the mainframe. For the experienced zOS developers, people that have never used Git needed training. We still get questions all the time, especially about rebase issues, about commit squashing. There's things that I don't know. I haven't been working for Git for 35 years. I've been working with JCL for 35 years. We have to ask a lot of questions, but the training and coming up to speed takes a while for people to get comfortable with, especially people that have been doing this for a lot longer than I've even been doing it. Really didn't trust this whole process, and they do now, which is fantastic, but it takes a while to get everybody up to speed and on the same page. The nice part about it is, like Suba said, we all use the same builds now. So we're all using the same Mac libs. We're all using the same, you know, options for compile, options for link, everything. So now we don't run into any problems where we check something in and it breaks in production because our development environment was different than production. The research and implementation took a good bit of time. This took us, what, Suba, well over a year, maybe a year and a half from the time we started till the time we went production. And this was only part-time on Suba's and iPark. This was, we had a full-time job, and this was just sort of for fun. And then we found out upgrades can cause some headaches. Git really changed when you went to, what is the latest zOS version, 2.4 or 2.6? It changed a lot of stuff, and it caused us a bunch of headaches. One of the things that really changed was Jenkins uses the non-interactive bash on USS, and the non-interactive bash just completely changed how it works. So it just stopped working. You couldn't find Git at all. Luckily, we caught this before anything bad happened and rolled back. But just debugging is the headaches, because our group's zOS people, and trying to sometimes dig into what's the root cause of some USS problems is really not our forte. But luckily, we have people in the company that are really good on the off mainframe Linux world, and they help us a lot with questions and answers, and did you try this and that? So if there's any last minute questions, we have about 2 minutes left. You're welcome. It was a good experience. We just wanted everybody to see this and see that it can be done. We presented this in Dallas Share a year and a half or a year ago now. We got really good feedback from it. I still get questions from people. If you want the sample libraries or you have any other questions for us, our emails are right here in the presentation. If you downloaded the PowerPoint, either one of us will be glad to answer questions or tell you how we do it, or send you a copy of our files so you can go through and play with the sample programs. Last but not least, our feedback. If you liked it, give us really good feedback so we can come back again. I haven't spoke at GSE UK since the late 90s. Last time I was talking about the coupling facility in the late 1990s. So it's wonderful to be back with GSE UK.
I was in high school at that time. It would be nice to present with you.
Yeah, thanks, Suba, for making us feel that much younger than we did 5 minutes ago. Yeah, we've already started planning what's going to be talked about at the GSE in person there, Kevin. So we are formulating what we're going to do. We're probably going to have a theme on each day, and certainly we'll let you know when we do the call for papers through social media what we're looking for. So that would be great to see you in real life. Thank you so much for the presentation. I think based on the number of questions, you certainly got people thinking, myself included, so some of those questions were from me too. Thank you so much for...
There's a new question.
Oh,
yeah.
It says, since you mentioned that it was part of the side project, it has now become, it is definitely an upfront and standard part of our environment. This is our production environment now. The great thing about it is, besides the upgrades that I mentioned, we don't have to do many changes. I mean, if we add a new module, we add it to the USS library and it picks it up automatically. If you add a new macro, it picks it up automatically. You might have to do an assembler dependency file if you're adding a new assembler. But other than that, there is not much maintenance from this build project. And then, of course, Jenkins is taken care of by another group, which is lovely. And our Artifactory is taken care of by another group, which is lovely. So we don't have to worry about any of that. This is our upfront. Suba and I are sort of in charge of it if there is an issue, but there hasn't been one, and it doesn't take much time.
It's been in prod for like 2+ years now, I believe.
Yes, almost 2 years. All right. Thank you, everybody.
Thank you, everybody.
Thanks, Stuart, for letting us do this.